Aha. Okay. What you see here, I don't see my screen very well. Let me fix that so I can see this a little better. Okay. Yeah, that looks good. Okay. This looks like a rectangle. It actually kind of looks like a square. It should be. But I have a 4x4. Okay. Now, it's actually not a square. That's its thickness. If I slice it off, let's say here, then I'm going to have a slice that's pretty thin here and pretty thick back here. Okay, it's thicker as I move back. So there's more mass per unit of this area up here than there is down here. Let's say we've got a function that gives me the mass per unit area. So let's start with just a really simple function, linear function. Of course, this is linear, but I've got some out there that have some simulated curvature. Okay, so let's just say we got a rectangle. You know, I can't start off like that. I was wanting straight line. Okay, let's try a straight line. Let's say this rectangle is 10, maybe in centimeters by 4. Now it doesn't represent what I just showed you, although we could suggest something there. And let's say we put this rectangle on a set of X, Y, coordinate axes. We got a density function. Density 2x plus 4y. And this is mass per unit area. Well, just for starters, I'm going to divide this up more or less equally into 41 centimeter squared. Then I'm going to pick a square. I'm going to work with the chalk and do most of them. Okay. So I'm going to randomly pick. Oh, I missed. Okay. At least I hit it at the right height. Try again. Oh, it was low, but I can take the intersection of those 2 points. Or, you know, projection lines. Okay, so projection lines. Take me to this square. How much mass is in that square? Figure it out. Approximately how much mass? Give me a good approximation. Okay, everybody got something between 24 and 26. I didn't get anything just to talk about 2 minutes. But looks to me like the coordinates of this point are, they're going to use this point. Okay, you might have used this point. You could use any point in the rectangle. You're going to get something pretty close. But if you use this point, which is what, 6, 2. Okay. And if X is 6 and Y is 2, you get 20. So you get something at least 20. If you go up to this point where this you know, X and Y are both maximized here. And clearly that's going to maximize this. It's going to be 7 and 3. Okay. Which is going to be 14 and 12 and 26. Okay. So you're going to get something between 20 and 26. Now, if I use this point, I'm about halfway up, but it's a little closer to this, and I'm probably going to be closer to 20 than I am to 26. Okay. Now, we see that the estimates if I did my calculation, then we're up to 20 to 26. That's at the lower left-hand corner. This is to the upper right-hand corner. In the gradient of this function, this what? What's the gradient? 2i plus 4j. So the gradient, not totally relevant to the integral, but we're actually getting the total amount. But the gradient and that would be over 2 and up 4 would be about like this. That's the direction of maximum increase. So if we go from here to here, we're going to get the maximum. We're not going to belabor that too much, but want to make that observation. Relevant to how you might sample the density. We're going to sample the density by using 1 point. Another observation I'll make while we're at this, and we just everybody got different estimates in different points. They didn't do that spontaneously. Yeah. You didn't all use the same point. That's good. If this area was much tinier, I'd squeeze these numbers a lot closer. If it was a millimeter, okay, then you probably have about 1/10 range, maybe less. These things don't have to be squares, and what I can say about what the optimal shape would be if you're really trying to approximate this, which you do a lot of times. And then you kind of want to take kind of a gradient to give it a shape. Not going to talk about that. But if you have 1 millimeter squares, then the range would be much smaller. Okay. Then you could say, well, okay, we did a millimeter square up here where the density is greatest. Maybe I would tend to get the maximum deviation I get from millimeters, so I pick I'd still maybe pick 6.9 and 2.9 is the lower corner and 7.3 is the upper corner. And I'd evaluate this as the lower corner. That'd be easy and it'd be related to your gradient in a way that you might want to think about. Okay, well, moving on to the real problem, which is estimating the total area, or at least the density of this, but the mass corresponding to this square. I'm going to estimate that as being that point as being And I can plug that in, that's gonna give me 12.6. That's gonna give me 9.6, it's gonna give me 22.2. I think. With a question mark on that. Doesn't matter, it's easy to calculate. Okay. I'll say delta M, our contribution to the total mass. It's 42.2 times our area. Our area of this increment is the unit. It's 1 square centimeter. Now, if I use a smaller area increment, I use the millimeter. Say millimeter square, somewhere around that. Then I do 22.2 times 0.01. Units of area. And I might even write down units. I like to do that. But right now, it's impressive. Okay. What I just did was this. You understand what that notation's telling us? It means that this is a random sample point within the area. And if the area increment is small enough, then this function doesn't vary a whole lot over the region. If both the delta x and the delta y for the region are small. In general, we're going to have a delta x and a delta y. In this case, delta x and delta y both be 1 centimeter, but in general, they're just going to be simple. Now we're going to start setting up an interval. This is what we always do when we develop an interval. We partition the region. How do we partition this region? By partitioning x and then partitioning y. It's not the only way we can partition the region. We can use polar coordinates and partition theta and partition r. And we're going to do that. So we partition the region. Then symbolize delta M for typical region. Well, there it is, it's symbolized. Okay, once we have our partition, we've pretty much got our interval. Or the sum of the delta M take a limit to get through. Okay, how are we gonna partition the region? Talk about that for a second. Yeah, first we partition X and Y. Okay. Let's pick X. Then. X goes from 0 to 10. So we partition this interval, 0 equals X1, which is less than X2, which is less than dot, 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 which is less than Xi minus 1, which is less than Xi, which is less than all the way out to X and so n, which is 10. Can you read that? There's smudge there. Okay. And well, that's what we're doing here for 1 centimeter. So, you know, X. X1 is X naught. X naught. Okay. X naught is 0. Xn is 10. If X0 is X naught is 0 and Xn is 10. And these things, each one of these is less than the other, and we're going to have a series of X values all the way from here to 10. In this case, there were 10 intervals, and they were all of equal length. So X1 would be, X naught would be 0, X1 would be 1, X2 would be 2, Xi minus 1 would be I minus 1, and Xi would be I, and Xn, X10 would be 10. And make sure we got that picture, because of course, n could be 70 billion. And we probably wouldn't want to do that one by hand. I'd be using a computer with this little desktop. Okay, so we've got this. Well, there's a picture. So at this point, forget about the 1 centimeter range. Right. Then the partition Y at Xi star. Okay, Xi star is in the interval. Be hard to read. I'm just saying, Xi star is between Xi minus 1 and Xi. It's in the I interval. Now, why do we do this? Well, in this case, it's going to be the same. Well, the Y interval is going to go from 0 to 4, no matter which X interval I choose. Okay. If this is the arc of the circle here, then the Y partition would be different. It would have different limits for different X's. Okay, so you want to kind of keep that in mind, but right now we'll keep it simple. So we're going to say well, what this thing was. Okay. Well, for X equals Xi star, Y goes from 0 to 4 within the region. Okay. Y values from 0 to 4 are all in the region. And any Y value that isn't between 0 and 4 doesn't give you a point in the region. That's an important thing to understand when this thing is no longer a rectangle. So okay. You might want to say then the interval be yi minus 1, then yi. But i's already been used for X. So we're going to use J. Let's see how that works. And we're not going to use the same number of intervals for Y that we use for X. We'll call this Y sub M. Okay, well, that's illuminating, isn't it? Okay. So I'll call it sub-region. It's sub-region. Xi minus 1 less than Xi. Yj minus 1 less than Yj. So, well, let's do a picture here. We've done the ith X interval. Let's just say that X equals Xi star from this dotted line. So this is implicitly the ith interval. Interval from this little rectangle. Y has also been partitioned on this interval. So we've got, I'm just going to partition on this interval. That's all I'm interested in. Okay, this X interval. Okay. We'll draw a picture. There's my, there's a rectangle. My sample point is X I star Y J star. Here. So now what I want you to do is write out the delta M for that region. It's simple. You don't know what the numbers are. It's going to be delta M IJ, two subscripts. Okay, well, delta MIJ could be just like this expression over here, which I probably don't have on the board, but I thought it was going to be like this expression, except with more information. So we try to put too much information in. Okay. Instead of X star and Y star, we've got a specific sample point. It's going to equal delta of X I star Y J star. And of course, then we can plug that into the formula for delta, whatever the formula is. In this case, it's a simple linear expression. I need a little more space, I think you can get it. Times. What are the dimensions of this rectangle? Well, my chalk keeps walking away. Okay. This rectangle has dimensions xi minus xi minus 1, which we will call delta xi. That's our definition. And this will be yj minus yj minus 1 delta yj. So understanding what we mean by delta xi and delta yj is width of this interval and height. We're saying writing this. Now, why do we write this? Because we want to write the area. And remember our expression was delta of x star y star delta x delta y. Comes after. Okay. Now, of course, that equals this. Use the formula. Well, total mass would be the sum from I equals 1 to n. Why do I say I equals 1 to n? Because I have initially just partitioned the ith interval. Okay. That would be this. the IFX interval partition. But since I could be anything, we can then take the sum of the small rectangles. And there we have it. If we sum from I equals 1 to n, that means now we've done it for all these rectangles. What have we done for each one? We've partitioned each one of these rectangular strips into tiny rectangles on which the value of the density doesn't vary a whole lot. And if we want to make them smaller, we just make n and m bigger, or intervals. Now, there's some restrictions, and when I learned this, we worried about those technicalities, but nobody's really worried about them now. Not sure that's a good thing. So we're just going to accept that we're not going to worry about the mesh and the partition and all that stuff. I'm going to say that as long as both x and y get tiny, this is going to work. And we get this limit. Okay, this means we're going to let the number of x intervals of x subintervals approach infinity in such a way that they all get tiny together. We let n go back to infinity by letting the first interval be this, and then a bunch of intervals here, right? They've all got to get small together. And then for each x subinterval, we do the sum for y. Now there's one more notation that didn't necessarily make sense before, but m is going to be maybe different for every vertical strip. There might be times where there are reasons to do that. We're going to call this m sub I. We're going to call this m sub I. This is the number of little rectangles that go to make up the ith strip. In any case, this approaches then the integral. Well, we partition the x interval from 0 to 10, right? So the x values go from 0 to 10. Go from 0 to 10. Okay, for given x strip, y is going to go from 0 to 4. So it's the interval 0 to 10 of the integral from 0 to 4. Of 2x plus 4y. Now we've got to be a little careful. And I was a little careless when I wrote this. I'm going to change one order here. This inner sum is a sum over J, right? So we probably want to write that Y increment as delta Yj within this expression here. And then delta Xy here. Now it corresponds better because what we have to do here is, well, this is Y going from 0 to 4, so our delta Yj will become dy's. And the X intervals from 0 to 10. So, an integral with respect to X. Well, that's an easy integral. Do it. One thing, just to be clear, I think you would probably do it because you're used to doing partial derivatives. This is an integral with respect to Y. X is constant. So treat X as a constant when you do the integral with respect to Y. Let's see what we got. Okay, well. This interval is then the interval from 0 to 10 of antiderivative of 2x plus 4y with respect to y. That means something. If we do the y derivative, we're going to get this back, right? So if you don't get this back when you do the y derivative, again, okay. So we're going to have 2xy plus 2y squared evaluated from, it may be a little low here, from y equals 0 to y equals 4, so you don't actually accidentally substitute for x. Okay. And well, that gives you gives you 8x plus 32y, 32x plus 32. Did that in my head. I go down to 720 here, and then I check. Okay, tell you how I checked it in a minute. And then that integral is very straightforward. It's going to be 4x squared plus 32x evaluated from 0 to 10. 10's easy. I'm going to give you 400 here. And this is 320, which is 720. Just for information to keep my head straight, I just integrated the 4y by itself and took it through and got the 320. And then I did the same thing with the 2x, integrating it through, got the 400. Then to check, I just went to my picture. This rectangle, center point of that rectangle would be 5, 2. Plug that into my density equation, and I got 18. Okay. This density equation is 2x, which would be 10, 4y, which would be 8, that's 18. And multiply that by the area of the whole region, which is 40. That works because the function is linear in both x and y. So I kind of confirmed my interval. I just took the density here and said, since it's linear, I think it's all going to work out. Now, if it wasn't linear, it was like x squared plus 4y. that would change things, and your density in the middle wouldn't give you an accurate result, although it might not be too far off. Okay. Well, you know, that integral would just as well give me the volume of this region. Okay. If the height is 2x, well, it isn't. You can imagine that region that got a height of 2 centimeters times whatever x is. Well, that's in this direction. Well, it'd be going up in this direction. Okay. And that's a little harder to show center from. And for y, okay, but be steeper, be kind of shaped like that. Actually, like okay. This could have represented the volume of a typical increment. Okay. You know, come back to here. And if this is like the base of that figure, then just take my saw, cut up 10 times over here and 10 times, 4 times this way, or whatever. Okay, then I get little cylinders. Each little cylinder still going to have the same Wobble vector, same slope, but the altitude isn't going to change very much if I divide this up into 40 little rectangles like that. Okay. So this expression could be z coordinate or altitude at some arbitrary. And then everything we did would represent total volume. Then we can do a more realistic integral for this volume. Based on measurements that we take, and we measure this thing, come up with the function of 2 variables. This models the height. And you already know how to get the tangent plane, so you pretty much got it. So you just take the equation of the tangent plane, solve for z, do the same thing, you got the volume. Okay, something else I wanted to say. No, not really. Okay, well, let's say now that we want to find center of mass of this thing. Okay. And let's say instead of the 2x plus 4y function, let's say it's 2x squared plus 4y. Okay. So well, the total mass is going to be, what right be the integral for the total mass. We've already subdivided everything. All that's changed is our density function. So you use everything we did, except we have to use this density function. Okay, well, everything we did is going to work. Mass is going to be. Approximating pretty close to 3,000. Less by 13 and 30. Okay. Be 2986 and 30. Something like that. Okay. And I have this thing in my head. Okay, now, if we want to find the center of mass, we've got to find torque about each axis. Which we're not going to have time to do all that. Let's find the torque. I don't know, you want the X or the Y axis showing either this or this? Oh, I don't know how you do that. Okay, X axis will be the torque about the X axis. That's simply just the mass. The IJ region times YJ star. Why is that? Well, because really good. Okay, there we go. That's supposed to work. Okay, I need. We'll do this pretty intuitively. That's pretty much not everybody have physics. But if I put this here, try to wiggle it. There's a certain amount of torque I need to support this, and I need to support torque to support the meter sticks. I'm just going to hold the meter stick in the middle, so I don't need any support. Okay, don't need any torque. And I'm going to put this over here. Okay, I can feel that weight. To put it out here, I feel a whole lot more. Okay. So the torque depends on the mass and how far you are from the fulcrum. The fulcrum in this case is the x-axis. So what we're looking at. Go ahead and use this direction, but it's already drew it. What we're looking at is our typical increment here. With our IJ increment. The coordinates of our sample point for xi star yj star in the area is delta xi by delta yj, right? We get our delta mij the same as we did. We take our delta function and evaluate it at our sample point. Then our partition, we have a delta x and a delta y. Multiply the density by delta x, delta y, our area. All we got to do to get the torque is multiply this by how far it is. This is our representative distance from the other axis, and that equals yj. What's that do to our interval? Some of the torques being a little careless. Okay. Some of our delta m's times yj star. Times your error. Same expressions we got before. Now fill in the sum. This is m equals 1 to n, and j equals 1 to n sub I. This approaches the integral. And there, I do that integral. Y quarter of your center of mass. Let's call this torque about the x-axis. Let's torque over the mass. Torque about the x-axis divided by the mass. And why that? Since torque about the x-axis is the mass times the y center mass. Okay. And that's just, again, the whole idea of torque. It's just now you got this whole rectangle being rotated about the x-axis. Whether that's intuitive or not, that's how it's done. That's an important integral. It's a moment integral. Moment integrals are extraordinarily important. And they're important in statistics, they're important in physics, on the next turn. All over the place. Okay. Even had a moment of inertia, I don't know which case to do, YJ squared separately. It's more than inertia before the R squared. We had physics, you probably remember what I'm talking about. All right. Okay, well, there you have it. Hopefully that'll prepare you to do the assignment. Email me if you have problems, and do read ahead because we're going to do a little bit of review next week as well. We're going to have the next two sections. So, and in the next two sections, you begin to see what happens if you don't have rectangles. And I think they get into the polar coordinates too. We'll talk about that quite a bit next time. Pay attention to the way I developed these. I said a lot of stuff that wasn't necessary. Just get, you're gonna go for a rectangle, you just slop that down. Okay, it's the whole idea that you partition X, and then you take that one part of your partition, one increment of that partition, and partition Y. And if you don't have a rectangle, the limits of that partition depend on whatever the function is. Okay.